Welcome back to Probability and Statistics 1. We're still here in Unit 3 discussing color sequences, and I wanted to end our initial discussion with it with a look at a property called independence that's going to play a large role in what we do going forward. Independence is a property that applies to both events in a probability space and to random variables. And as I said, that property exists in the color sequence model. And I want to take a minute to show you where and how it exists, and then use it as sort of motivation for a discussion that we're going to have soon about independence, and also as a stepping stone to the idea of a Bernoulli process, which is a generalization of the color sequence process. So let's see what we have in store. The property of independence is one that appears very often in probability theory, and it manifests itself in the color sequence process in terms of these indicator variables that we've been studying, the I sub k's, right? I sub k is 0 if draw number k was a green ball, it's 1 if draw number k was a red ball. And these variables as a group, if you consider them all together, they exhibit this property called independence. So I want to kind of go through how that happens. Informally, we say that two events are independent if knowing that one occurred has no effect on the probability that the other occurs. So, for example, you could consider two events like the event that there's a dust storm on the planet Mars in the vicinity of our current rover that's up there, with a little helicopter and everything. Let's let that be event number one, and let's let event number two be the event that there's a dust storm at my house on High Street in Farmville. If somebody told me that, yeah, there's a dust storm on Mars right in the vicinity of that rover, would that alter the probability that I would assign to the event that there's a dust storm at my house? Probably not, right? Those events are, even if it's 100% likely that there's a dust storm on Mars right now, that would have nothing to do with the likelihood of an event of a dust storm at my house. So we would say those two events are independent. On the other hand, if somebody told me, it's raining at Hampden-Sydney College right now, that would affect my likelihood. It affect the likelihood that it's raining in Farmville. Those events are not independent, right? If it's raining at Hampden-Sydney, that tends to increase the likelihood that it's raining in Farmville. So events can be either independent or dependent. And I want to show you, as I've said, this case in the color sequence model where we do have independent events. So to do that, I want to introduce this operation, which I'm just denoting with a circle here, called concatenation. And concatenating color sequences is just like concatenating strings. You just kind of juxtapose them. So, for instance, the color sequence 0, 1, 0, 1 concatenated with 0, 0, 0 would yield the color sequence 0, 1, 0, 1, 0, 0, 0. So you just put them together like that. And it just gives us a way of talking about dividing a color sequence into two halves, one half followed by another half. So an interesting property of the color sequence model is talked about here in Theorem 3.15. It says, let I1 and I2 be any two finite color sequences from the color sequence process with replacement, then the probability that the concatenation of those two sequences occurs, that is, the probability that you have the first sequence followed by the second sequence, turns out to be just equal to the probability of the first sequence times the probability of the second sequence. And in some of the discussion questions that come up, I ask you to verify that. And for instance, if you just look at that first discussion question, and just forget about Theorem 3.15 for a moment, and just look at the probability of the sequence 0, 1, 0, 1, 0, 0, 0, and compare that to the probability of 0, 1, 0, 1, 0, 1, and the probability of 0, 0, 0, you'll see that the theorem is true, or at least in that case it's true, right? That the probability of the concatenation is the product of the probabilities. And the proof is actually really simple. I mean, we know that the probability of a color sequence is the success probability p raised to the number of ones times the failure probability 1 minus p raised to the number of zeros power. And so if you think about a concatenation, right, I1 composed with I, or concatenated with I2, how many ones are in that? Well, it's just the sum of the number of ones in the first sequence and the number of ones in the second sequence. So similarly, the number of zeros in the concatenation is just the number of zeros in the first sequence plus the number of zeros in the second sequence. So the probability of the concatenation is given by this formula here. The exponent on p is the total number of ones in both sequences together, and the exponent on 1 minus p is the total number of zeros. But then just using properties of exponents, you can write that as in the way you see here on the second line, p to the number of ones in the first sequence times 1 minus p to the number of zeros in the first sequence times p to the number of ones in the second sequence times 1 minus p to the number of zeros in the second sequence. But we recognize that as just the probability of the color sequence I1 multiplied by the probability of the color sequence I2. So it's a really simple theorem to prove. And then it has some consequences, though, that are not quite obvious. And these discussion questions ask you to go through this. So in the first one, as we mentioned, reduce this thing fully. Actually, I could apply theorem 3.15 one time, and I would get, I could get a product of 2 probabilities. But then I could apply it again. So the idea in this first bullet point is to apply theorem 3.15 repeatedly until you can't apply it anymore, and see what you come up with. I think you'll find the result interesting. Second thing is just to re-express that sequence in terms of indicator variables. And then the third bullet point is to look at this in terms of indicator variables. In other words, use that theorem to reduce this guy fully. And number 4 is a similar kind of thing. And if you do those exercises, you won't be surprised to see our theorem 3.16, or I should say corollary 3.16, which says that essentially, if you look at any intersection of events that are expressible in terms of the indicator variables, the probability of that intersection is equal to the product of the probabilities of the individual events. That is the property of independence. Events are independent if the probability of the intersection is the product of the individual probabilities. That's what we mean by independence. And it's a little unclear at this point sort of why we should care about that. But we'll be able to see that that's actually a property we should care about when we study it a little bit further. But right now, I just want to get it out there as a property that is apparent in the color sequence process when you look at the indicator variables. By the way, the property doesn't hold for some of the other variables we've considered. For instance, it's not true that all the binomial variables we've considered are independent in this sense, but it is true for the indicator variables. And that property, that the probability of an intersection is equal to the product of the probabilities, is called the property of independence that you see here. So I want to use that as sort of a stepping stone to the notion of a Bernoulli process. A Bernoulli process is a generalization of the idea of a color sequence process. So a color sequence process is a Bernoulli process, but there are other Bernoulli processes as well. And let's see what that's all about. So in definition 3.17, you have the definition of a Bernoulli process. And it's going to be familiar to you because of all the work we've done with the color sequence process. At least some of the ingredients will be familiar. So we start out with a set of indicator random variables. Those are the I sub k's. They're just like the indicators for the color sequence process, except now they might be indicating something other than colors, right? But they have similar properties to our indicator variables. That is, the indicator variables I sub k indexed over all integers k, over all positive integers k, have the property that the probability that I sub k is 1 is going to be equal to this certain number p, and the probability that I sub k is 0 is equal to 1 minus p. So I sub k takes on values of 0 and 1, and the probability of a 1 is p, and the probability of a 0 is 1 minus p. And that's true for all k. So it does, the probability, p, we're going to still continue to call the success probability, and that doesn't depend on k. And actually, I sub k we want to think of as the indicator of a success. And here a success is just whatever a success happens to mean in the context of whatever problem we're dealing with. For the color sequence process, a success was drawing a red ball. But now a success could be just about anything. But the indicators are indicating successes. So successes occur with probability p and are indicated by a 1 for the corresponding I sub k, and failures happen with probability 1 minus p, and they're indicated by I sub k being 0. And then the second main ingredient for a Bernoulli process is that these indicator variables have that property of independence that we saw back in Corollary 3.16. That is, any probability involving an intersection of events involving the I sub k's would be the product of the probabilities of the individual events. That's the property of independence. If those two things hold, then we say we have a Bernoulli process with success parameter p. And Bernoulli processes, as I said, are much more general than the color sequence process. They can represent things, well, like the color sequence process, but also coin flipping, dice tossing, and many other examples. And so after we learn a bit more about independence, we'll study the Bernoulli processes further. So that's going to end our initial discussion of the color sequence process, and it kind of opens out into this larger vista of Bernoulli processes. We're going to do a few more applications with Bernoulli processes, which we'll talk about in class, and then we're going to launch into a discussion of independence next. So thanks for your attention, and we'll be coming back at you real soon.